Today, we're diving into a topic that sounds super complex but is literally all around us: radiation. We're going to decode how it's measured and finally make sense of all those confusing units you hear about.
You know, if you've ever heard terms like sieverts, curies, or rads and felt your head start to spin, you are definitely not alone. The language of radiation can feel like you're trying to learn a whole new alphabet, right?
But here's the good news. There's a pretty simple logic to it all. So in this explainer, we're going to crack the code together. We're going to turn that confusion into clarity, and by the end, you'll have a really solid grasp of what these terms actually mean.
Okay, so here's our roadmap. We're going to use this simple little mnemonic, R-E-A-D, to trace the path of radiation all the way from its source to its effect. And then we'll bring it all into focus by looking at how this stuff shows up in our daily lives.
The absolute key to understanding all these different units is that READ mnemonic. It stands for radioactivity, exposure, absorbed dose, and dose equivalent. This simple acronym is going to be our guide through the whole process.
And what's so useful about this is that it's not just four random terms. No, these steps actually follow the logical path of radiation itself, from the material that releases it, to how it travels, to what actually gets into your body, and then, finally, the effect it has. It's a complete journey.
All right, first up, R for radioactivity. This is square one, the source of it all. We're looking at the radioactive material itself, before the radiation has even gone anywhere.
So radioactivity is all about how hot a source is. It measures the rate at which atoms in a material are decaying and literally throwing off energy. And we are specifically talking about ionizing radiation here. You know, the kind with enough punch to knock electrons out of atoms, which is what gives it the potential to cause biological change.
And to measure this, we use two main units: the curie, which is part of the common system you'll probably see more often in the US, and the becquerel, which is the international standard. But here's the key: they both measure the exact same thing, which is just the activity of the source.
Next up is E for exposure. So once that ionizing radiation is released from its source, we need a way to measure it as it's traveling through the air.
This is what a radiation detector, like a Geiger counter, or maybe one of those film badges that a worker would wear, would actually measure. It's not about what's been absorbed yet, just what's present in the environment all around you.
The units here are the Roentgen, that's the common unit, and the Coulomb per kilogram, which is the international one. So if you ever hear a measurement in Roentgens, you know someone is talking about the amount of radiation that's just present in the air.
Now we get to A for absorbed dose, and this is where it starts to get personal. We're no longer just measuring what's in the air. We're measuring the energy that actually gets deposited into an object, or, a person.
So the key distinction here is that exposure is what you walk through, but the absorbed dose is what you actually soak up. It's the measure of the energy that radiation leaves behind in your tissues.
For this, we use the RAD, which pretty fittingly stands for Radiation Absorbed Dose, or its international counterpart, the gray. When you see these units, you know we're talking about the energy that's been absorbed by a body.
Finally, we arrive at D for dose equivalent. And this is arguably the most important measurement of all, because it answers that crucial question. Okay, I've absorbed this radiation, so what's the actual biological risk?
This step is so critical because it adjusts the absorbed dose based on the type of radiation. It accounts for the fact that some types of radiation are just more biologically damaging than others, even at the same absorbed dose.
And this gets to the absolute core idea. For instance, heavy alpha particles do more concentrated damage over a short distance, kind of like a bowling ball, while lighter beta and gamma rays are more like ping pong balls spreading their energy out. The dose equivalent calculation uses a quality factor to account for this difference, giving us a much clearer picture of the potential health effects.
And the units for this are the ones you most often hear in the news when health effects are being discussed: the REM, which stands for Roentgen equivalent man, and the sievert. These tell us the real biological risk.
Now, after all that technical detail, there's a really handy simplification. For the most common types of radiation we encounter, beta and gamma, that quality factor is 1. This means the numbers for exposure, absorbed dose, and dose equivalent are essentially the same. So for practical purposes, 1 Roentgen is roughly equal to 1 rad, which is roughly equal to 1 rem. This makes things much easier to track in a lot of situations.
Now, let's put this knowledge to work. These units can feel a little abstract, so we're going to ground them in reality. We'll use the millirem, which is just 1,000th of a rem, to look at the doses we receive in our everyday lives.
So what does 1 millirem of dose equivalent feel like? Well, you get about that much from taking a single coast-to-coast flight, all because of the increased cosmic radiation at high altitudes.
Or you could get the exact same dose just by living for 2 days in a high-altitude city like Denver, which has higher natural background radiation than cities at sea level.
And this really shows how common these small doses are. That same 1 millirem dose is what you'd get from living in Atlanta for 3 days, from watching TV for a full year, wearing an old luminous watch for a year, or even living next to a normally operating nuclear power plant for a year. The takeaway is that we're constantly exposed to tiny, manageable amounts of radiation from a whole variety of sources.
So we've cracked the code, from radioactivity at the source, to exposure in the air, to the absorbed dose, and finally the dose equivalent that tells us the health risk. You now have the tools to understand this invisible energy. The question is, now that you can read radiation, what news report, medical procedure, or everyday object will you see differently?